Okay, folks, this is going to be, we're going over Copeland pages 165 to 167. We've done steady flight, a simple version, and then a more complex version where the forces and mechanical forces acting on the aircraft are not aligned, so we create moments. This is um, an example of a steady climb. So steady climb means constant velocity and an angle that's not changing. Okay. Now the reason why it goes through all of this, and it's quite there's quite a bit of working out, is basically it's just trying to show you how the equations that are derived for working out angle of ascent for an aircraft, an angle of descent. Okay, and there's quite a simple formula, but it's just showing how it's derived. So if this is all a little bit too complicated for you, try and stay with it. And then we're going to look at the examples in the next video of working out for a given descent angle, how far you have to travel before you land, etc., for glide angles and all that sort of stuff. So that is what this is for. Okay, so I've done the diagram on the board. You can see here that with all of the moments that are generated for this aircraft when it's actually climbing, and it's climbing this way. Okay, so your angle is here. Now they've started with assumptions that the angle of flight is the same as the thrust angle. Okay, now we know from our level flight the thrust angle is actually angled up slightly from the direction of travel. Okay, but for this example, they've said we're not going to worry about that too much. It doesn't change it too much. And the drag and thrust are acting through the center of gravity. So we're ignoring some moments that might be happening as well. Okay, but this formula is one that can be used as a rough estimate. And that's why he's just showing you how it is derived. I've done my forces in black on this diagram. So you can look in the Copeland textbook on page 166 if you want to see this diagram in person, and distances I've done in green, okay, for calculating moments. So the other thing you need to understand is that it's kind of like the wheelbarrow situation. Rather than using true moments and perpendicular distances, he's made sure that the forces acting are perpendicular to that angle, okay, so at 90 degrees to the angle going up. And that's how he's calculated his moments, okay? So that's the next thing you need to understand. So we'll just go through the equations. First equation that's on page 166 is he's worked out sum of forces perpendicular. So he's done this, because it's the angle that's going up. Up is positive, and he says the sum of forces perpendicular is equal to 0 because it's a steady state climb. And then he said 0 equals lift of the wing because it's going up, minus lift of the tail because it's going down, minus W cos theta. Now that W cos theta is this component that is perpendicular to that angle. Okay, so it's very much like when you have a weight on a plane, weight acting into the plane, mg cos theta, weight acting down the plane, mg sine theta. Okay, that's how they've got that W cos theta. Okay, so your first equation comes to W cos theta is equal to the lift of the wing minus lift of the tail. Okay, so they've labelled that as equation 6 because they've gone through all of the equations in order from the steady flight examples, but I'm just going to call that 1. Okay, that's our first equation. Then acting along the plane, okay, we have to the right is positive, sum of forces parallel, okay, is equal to 0 once again because it's a steady state situation. And we end up with 0 equals drag, because drag is acting to the right, so it's positive, minus the thrust, because it's going to the left, plus W sine theta. And that is that weight component here acting in line with the angle of climb. Okay? That gives us a final equation of W sine theta is equal to T minus D. I'm going to call that equation 2. Okay. And then he takes moments, okay, about the centre of gravity. So sum of moments about the C of G is equal to 0. So 0 equals, he said, lift of tail times this distance to the centre of gravity, xt, parallel to the angle of ascent. Okay, so it's a bit like the wheelbarrow problem. So it's LT times xt minus lift of wing times xw, because xw is this distance here. Lift of the wing is going to make us rotate around that centre of gravity counterclockwise. This one is going to rotate us clockwise, which is why the lift of the tail is positive and that one's negative. So we end up with LT equals, so LT times XT, distance of the tail, is equal to lift of the wing times XW. Okay, what they do after that is they just divide equation 1, which is this one, by equation 2. Okay, so for the next step, we say equation 1 divided by equation 2. We basically put one over the top of the other. So, 2 over 1, because we want to get sine over cos, which is tan. Okay, so we go 2 divided by 1. Okay, so in this example here, we end up with an equation that is W sine theta over W cos theta, which is the angle of ascent, is equal to this one here, T minus D, over equation 1, which is LW minus LT. Okay? And we know that LW minus LT is going to be the total lift, okay? Because the total lift is those two vectors, one going down, one going up. Okay, so we can simplify this equation. We know that sine over cos, these two cancel out, the weights cancel out. We know that sine over cos is tan, so we end up with tan theta is equal to T minus D, thrust minus drag, over lift, because this, lift of wing minus lift of tail, is equal to lift. Okay? And then we finally get to the final equation, which is on page 167. Okay? And this is the thing that you're going to be working with to do the examples. So if you get anything out of this, it'll be this equation, okay? Which is theta, okay, which is the angle of climb or descent, is equal to thrust minus drag over weight. Now that is because it says here for small angles, so this is a little caveat for this equation, okay? It only works for small angles, so say a jet airliner that's taking off very gently. You're not going to use this equation for fighter aircraft and all that sort of stuff, okay? But it says here that you probably notice you've got a weight on the bottom here and you've got a lift on the bottom here, okay? That is because they say that lift approximates weight for small, so lift equals W for small theta, and tan theta is approximately equal to theta for small angles as well. Okay, so this equation is what we are going to be using in the examples, okay? Theta, which is the angle in radians, okay? So this is in radians, is equal to thrust minus drag over weight, okay? So pause the video, or actually you might want to go into Copeland and copy down this diagram and those equations, okay? And make sure you understand how that equation is derived. But if you take anything from this situation, make sure you understand that equation, okay? And we're going to do the examples. And there's one more thing for that. We have the value of radians, because you're using radians for this type of equation. So you maths heads won't have a problem with this, but a radian is 57.29 degrees. So we might want to write here 1 radian is equal to 57.29 degrees, okay? So in the examples, I'll show you how to convert to degrees once you've got a value in radians, and we'll do the examples in the book. I haven't seen too many of these equations in the HSC, or these questions in the HSC, but you just never know when there's one that's going to pop up. So that is a good equation to remember, if at all possible, okay? Theta, the angle of climb for small angles, is equal to thrust minus drag over weight, okay? This equation needs to go in your memory banks, okay? That's it for this lesson. I shall, or this video, I shall now eradicate this from the board, and we'll do the examples that are in the actual textbook. See you next video.